right, we are live. So in this lecture, I'm going to cover equation solving using the root function. And this is kind of based on basically the Newton's method and the secant method that you guys worked on in the previous homework. This is just a more advanced version of the same algorithm. I'll give a supplementary lecture where I cover some issues with equation solving, but let's just go through examples. So once again, we're going to import numpy as np, and then from scipy, and now we're going to use the optimization library. We're going to import the root command. Let's make sure everything's good. So let's start out by solving an equation. So we're going to just solve something really simple. So let's say define f of x, and what we're going to do is solve 3 times x minus 2 is equal to 0. So that's going to be our return value. So let me just come up here. So in general, with the markdown, if we're solving an equation like 3x is equal to 2, right? So what we have here is an equation where on the left we have some terms, and on the right we have some terms. Now, if you were to design an algorithm to solve it, you would actually have to have an import for what's on the left of the equality sign and also what's on the right of the equality sign. So it's just simpler to just rewrite this equation as 3x minus, as 3x minus 2 is equal to 0, or 2 minus 3x is equal to 0. And so the nice thing about these is these are kind of basically everything's on the right, on the left of the equality sign, or basically on one side of the equality sign. It doesn't matter. This is just a sign difference between this one and this one. But this allows us to simplify more complex expressions. And basically every expression you can get in this form of f of x is equal to 0 when you're trying to solve an equation. All right, let me just delete that out. So we're solving 3x is equal to 2, or 3x minus 2 is equal to 0. And so what we're going to do is have a solution, and then we're going to take root, right? So we're going to try to find the root of this function, and the root is the 0 of the function. And then similar to Newton's method, we have to give an initial guess. So this is a linear equation. Actually, this is something even more trivial, but you could use linear algebra to solve this. But I often find, just because I'm lazy, that I just let the root command do it. So I don't want to reformulate this as like a matrix type equation. We're not really going to cover too much linear algebra in this class, but it's easier just to write your function and then do the root. And then we can print the solution vector. And so what you're going to find here is, so again, we're taking the root of the function f. We have our initial guess, we have our solution, and sol actually gives us a bunch of different things. So it tells us what the derivative is the Jacobian, the solution, right? We get to 0, it tells us that it converged, it took n function evaluations. I think this is an estimate of the error. Actually, I don't know what r is. Status 1 means it's good, success is true, and here's the answer. So in general, we're going to be much more interested in these last two ones because root finding doesn't always work. So if we want to print the solution, we're going to print, if we did print sol of x to access this value. Next week, or pretty soon, I'll talk about classes, and this will be a little bit more explicit. But we get back the value, and it gives it back as an array because it assumes, in this case, x is going to be an array. So if we want the number, we could just print x of 0, and then we have our kind of value. So we could also do another function. We could do like g of x. We could do something like the homework problem where we do n log of x plus x is equal to 0. And then we do sol is equal to root of g. I'll give it guess of 1. And then we can print sol.x of 0 to get the solution. And in this case, we get 0.567. So again, we have a return value. We have our initial guess, and it's always assuming that it's an array coming back. So we're going to grab the first element of the array because we know there's only one element, because if not, I get back that array. And it depends if you want to work with a scalar or an array. Even though this is technically a scalar, this is actually a one-dimensional array, so it's a little bit different variable. So one other thing is these initial guesses can be important because you can get basically multiple solutions. So let's consider this function. So if I define f of x is, I'm going to do x squared minus 1. Actually, let's do x squared, yeah, minus 1 is equal to 0. So I want to do x squared. Let me put this up here, sort of cell above. Let's go to markdown. So basically what we're solving here is x squared, and I did the square command wrong, so I want to do squared, is equal to 1. And so I know x is going to equal to be plus or minus 1 because I actually have two solutions here. And the root command's actually not going to find both of these solutions. It's going to find the one closest to the initial guess, depending on the algorithm. And I'll sketch out a little bit later, just kind of give you on a piece of paper how the algorithm works, but let's just take a look. So if I do sol is equal to root of x, root of f, and I pick the, let me pick something like 5, right? I don't want to pick exactly this known solution. So I do sol dot x of 0. And what did I do wrong? Oh, I forgot the return argument. And I don't need the 0 there. And so I get back the 1 solution, right? But if I pick minus 5, I get back the minus 1 solution. So it really depends on where the initial guess is, whether you're getting the positive or negative. Basically, in this case, is if I pick something bigger than 0, right, I'm going to get back the positive solution. And if I get something slightly less than 0, I get back the minus solution. If I actually pick 0, the algorithm's not going to work. It's going to give me back 0, which we know is not a solution. So I could do sol.success. And in this case, I have a false. And the reason why is we have actually a 0 derivative at that value. And I'll explain that a little bit later. So the other thing we can do is also, in addition to solving nonlinear equations, right? So in general, nonlinear equations can have lots of different answers. Is we can also do multivariable equations. So again, here the number of equations has to equal the number of unknowns. So I could do define my fun. I'm going to pass in z. And so maybe let's solve the function 3 times x plus 4 times y is equal to 1, and maybe 2 times x plus 6 times y is 2. Yeah, that should work. Minus 2 is equal to 0. And so what I'm going to say, this is equation 1, and then this is equation 2. And what I'm going to do is unpack the variables in z. So z is a vector, so that's going to be, in this case, it's going to be assumed to be a 2-dimensional vector, and I'm going to unpack the values into y and x. And then I'm going to return equation 1 and equation 2. Now I could have equivalently done this as, let's do my fun, 1 of z. And if I want to do really shorthand, I could do 3 times z of 0, right? That's my x, plus 4 times z of 1, right? Minus 1. And then I could do my second equation, 2 times x z of 0, plus 6 times z of 1 is minus 2. And then I'm not even defining the equation. So this would be super shorthand. I tend to like writing it out. It's just easier to debug. And when I see like 0 and 1 and 0 and 1, it kind of gets hard for me. Because typically you're copying this down from a piece of paper. You have a set of equations you want to solve that have known variables. And so it's easier just to unpack them. So it really doesn't matter. So I could do sol is, again, root of, let's just do my fun. And now I have to give a guess. And I have to give 2 guesses, right, an array. And this actually allows it to know that everything's works well because it's a 2-dimensional array which tells root that it expects 2 equations being returned. So I can print sol.x, and I'm getting back my answer of minus 0.2 and 0.4. Or I could have done my fun 1, which is equivalent, and I get back exactly the same answer. If I want to look at the first one, I could get back the answer sol of x. Just one kind of shorthand notation. So in Python, right, when we set sol, right, equal to the root of my fun 1, what we're doing is actually setting sol as kind of the return value. So rather than doing this, I could have actually just done print, and this kind of gets a little bit weird. I've done print sol of x, and I'm getting back the answer, right? So this was my sol value, and here I'm grabbing the x value out of it, and if I wanted the first one, I could even go like that of x of 0. So this is kind of a Python shorthand that you might see, right? But again, I enjoy writing things. I think it's better just to write it out explicitly, just so you can see everything, rather than trying to do all the shorthand notation that I just showed you in the previous example. So that's kind of an overview of the root finding command. You can use this on fairly large systems of equations as long as there's no differentials in them. As long as we're doing algebraic equations, we could do nonlinear equations. We can do equations that are complicated, right? Log x squared minus 1. In your homework, you're going to have a reactor example, right, where you're going to have exponentials and things like that. But it's a pretty powerful function. Often the biggest thing is choosing the initial guess for the function, because let's just come back up here. Where'd I go? Where's the log one? Right, so for this answer to make sense, I have to have a positive value, but if I take a negative value, it might actually crash. Yeah, it's going to crash because, you can't take the log of a negative number. So that gives us an answer. But in some cases, like the efficiency of whether you can find something is really dependent on how well the initial guess is. This tends to work more in the case of really large systems. Like if you think about, flow sheet simulators in chemical engineering, often you're solving thousands of coupled equations. Coming up with those initial guesses can be hard. But in our case, we're only going to do a handful of equations, so it's not going to be that difficult. We will, when we get a little bit later, when we get to boundary value problems, we'll do like 100 coupled equations or maybe 1,000. But in those cases, it's relatively straightforward to come up with reasonable initial guesses because they're all roughly the same. All right, with that, I'll stop. Once again, if you have questions, just post them in the comment section, put them in Piazza, and I'll do my best to answer them as soon as possible. Thank you.